So in this video, we're going to look at the last type of intermolecular force, and that is a hydrogen bond. So firstly, let's have a look at how we define a hydrogen bond. It is a strong dipole-dipole attraction. So key thing there, it's very, very strong. So it's the strongest out of the three types of intermolecular bonding, okay? So it's a strong dipole-dipole attraction between an electron-deficient hydrogen atom. So let me just explain the electron deficient part. If you're deficient in something, you're lacking in it. So electron deficient means that the hydrogen atom is lacking in electrons. So that means that hydrogen atom there is going to have a delta positive on it. Okay, so electron deficient H atom means it's a hydrogen with a delta positive. So it's between an electron deficient hydrogen atom on one molecule. So remember, it's between different molecules. So it's the H delta positive on one molecule and the lone pair on a nitrogen, oxygen or fluorine on a different molecule. So if the nitrogen, the oxygen and the fluorine have a lone pair, you are going to find a hydrogen bond between the lone pair on one of these and the hydrogen delta positive on another molecule. Okay, so let's now have a look at that. So that means if the molecule contains nitrogen, oxygen or fluorine, you are likely to have hydrogen bonding between them. Okay, so the first example I'm going to do is HF, so hydrogen fluoride. So there is a lone pair, actually more than one lone pair, but there's a lone pair on the fluorine over here. Fluorine is very electronegative, it's the most electronegative atom, and therefore there's definitely be a dipole going across this molecule here. Okay, and if I get another HF molecule, so again lone pair on this one, delta positive, not delta positive, delta negative on this one and delta positive here. Okay, so a hydrogen bond is between the electron deficient hydrogen on one molecule and the lone pair on a fluorine, oxygen or nitrogen on another molecule. Okay, so there's clearly going to be a hydrogen bond between here. To draw a hydrogen bond, we use a dashed line like that. Okay, so it's between the H delta positive and the hydrogen bond must go to the lone pair on the fluorine over here. Okay, and then make sure you label that as your hydrogen bond. Okay, and that is our hydrogen bond, or that's how you should show in a diagram the hydrogen bond between two molecules of HF. Let's have a look at another molecule that has hydrogen bonding between it, and that is ammonia. So ammonia, pyramidal shape. Okay, I'm going to draw another one as well. Okay, nitrogen is electronegative or more electronegative than hydrogen, and therefore you have a delta negative on the nitrogen, and each hydrogen has a delta positive. So I'm going to do the same thing on this one. Okay, hydrogen is always going to be delta positive. You never have a delta negative on a hydrogen. And now we've got hydrogen delta positives on one molecule, and we have nitrogens with lone pairs on another molecule. Okay, so we want to show the hydrogen bond between that. So again, we're going to use a dashed line, must go from the lone pair on one nitrogen to the H delta positive on another molecule. Okay, and again, make sure you label that as your hydrogen bond. Okay, like so. So ammonia molecules do have hydrogen bonds between them, and let's look at the main one, which is our water molecules. Okay, so water also has hydrogen bonds between them. As we know, the central oxygen has two lone pairs on it, and oxygen is more electronegative than hydrogen, so we have a dipole going across these molecules. So each hydrogen is a delta positive. If we're going to show a hydrogen bond with another water molecule, again, don't forget to draw the lone pairs on oxygen and the dipoles, oh, not positive, across them. Okay, and again, the hydrogen bond should start from the hydrogen delta positive going to the lone pair on the oxygen. So again, a dashed line, and then label that as your hydrogen bond. Okay, and that is how you would show the hydrogen bond between water molecules here. Okay, don't forget that, you know, all these molecules do also have London forces as well. All right, we're going to focus a little bit more on water, because the hydrogen bond in water gives hydrogen, not hydrogen, it gives the water some very special properties. Okay, the first property that you may or may not know about water is that in the solid form, so solid water as in ice, so the solid is less dense than the liquid. Okay, and that's quite an unusual thing. Okay, usually something in the solid form is more dense than the liquid. As we know, ice floats in water. Okay, so that means ice is less dense than water in the liquid form, and that's quite a special property to have. Okay, the reason for that is, if I just draw another water molecule here, okay, it's worth noting, so I'm just going to draw the dipoles in as well. It's worth noting how many hydrogens water can make, hydrogen bonds that water can make, okay? So each lone pair, so oxygen has 2 lone pairs, each lone pair can form a hydrogen bond. So I'm not going to draw the other water molecules in, but that one can form a hydrogen bond. This one can form a hydrogen bond. Each hydrogen can take part in a hydrogen bond. Okay, so one water molecule can participate in 4 hydrogen bonds. Okay, so they can make 4 hydrogen bonds. And in the solid form, as we know, that's when we have maximum or the most intermolecular forces. So that means in that case, water is going to make the maximum number of hydrogen bonds that it can. Okay, if we look at our oxygen here, once it's taken part in hydrogen bonding, if we look at the central atom, being oxygen, oxygen has 4 bonding pairs. So now these are not lone pairs, they're taking part in bonds. So it then has 4 bonding pairs and 0 lone pairs. So if we have 4 bonding pairs and 0 lone pairs, you guys should know that that is going to adopt the tetrahedral shape. Okay, so when in solid water, so when in ice, all the hydrogen bonds form, water adopts the tetrahedral structure. Okay, so everything is held in a tetrahedral structure, and it's what we call the open lattice structure. So the hydrogen bond holds the water molecules in an open lattice structure in a tetrahedral formation. And what that means is that those water molecules are actually held further apart. And because they're held further apart, it makes the solid water, the ice, less dense than the liquid. Okay, so the hydrogen bonds hold the water molecules apart, making the molecule less dense than it is in the liquid form. Okay, it's also worth pointing out that because of the hydrogen bonds, so remember hydrogen bonds are very strong intermolecular forces, because of those, water has quite a high melting point and boiling point. Okay, so it has a high melting point and boiling point. As we know, the boiling point is 100 degrees Celsius and the melting point is 0 degrees Celsius. And that is due to the hydrogen bonds, okay? Because the hydrogen bonds require more energy to break, it makes the melting point and the boiling point a lot greater than what we'd expect. If water didn't have those hydrogen bonds, the melting point and the boiling point would be much lower. And to be honest, if the melting point and the boiling point of water was lower, life on Earth probably wouldn't exist. Okay, we wouldn't have water in the liquid form, which we need in order to survive.